let's now discuss how we find the domain when a variable is in the radicand. The domain of a radical function will have restrictions if there is a variable in the radicand, since the radicand must be equal to or greater than 0. So if we had the square root of positive 25, that would be equal to positive or negative 5, both of which are real numbers. But if we tried to find the square root of a negative number, we would get an imaginary number. So remember, the radicand, the number underneath the radical sign, must always be 0 or greater. So if we're looking at a graph, let's say we had f of x is equal to the square root of x. The domain is x is greater than or equal to 0, since, again, the radicand cannot be negative. So it starts at 0 and becomes more positive. But this domain will shift if we add a number under the radical. So the square root of x plus a would shift the domain to negative a. Why is that? If x were negative a, we would get f of negative a is equal to the square root of negative a plus a, and that would be 0. So x is greater than or equal to negative a. But it cannot be anything smaller than negative a, since this would then become negative and then create an imaginary result. So if this shifted and x were a, we would get the square root of a minus a, which is 0. So x can be greater than or equal to a. So this is how the radicand creates restrictions on the domain, since the radicand has to be 0 or greater. Now the domain of the function will not be affected by a constant on the outside of the radical term, since this will shift the function either up or down. So for f of x is equal to the square root of x, if you add a constant on the outside, this affects the y value. F of x is directly adding c to its value. So at this particular x, it would shift up c amount. At this particular x value, it would shift up c amount. So the entire graph shifts directly up, but it does not shift left or right. That would affect the domain if it goes left or right. But it goes up if you're adding a constant on the outside, and it goes down if you are subtracting a constant on the outside for the same thing. So this again would not affect the domain. Now, one scenario to be aware of is if there is a fraction. To find the domain of a fraction, find the domain of both the numerator and the denominator. The final domain will be the numbers that overlap both sets. So now in this example, we have a radical and a variable in the denominator. So we have to apply both restrictions that we've reviewed. So f of x is equal to x plus 1. In the numerator, there is no restriction. X can be any negative number or any positive number, and you'll get a real number in the numerator. So the domain in the numerator is negative infinity to positive infinity, or all real numbers. In the denominator, we'll have some restrictions. Since x cannot equal negative 2 or positive 2, since both of these will lead to this radical equaling 0. Now a radical can equal 0 if it's in the numerator, but since it is in the denominator, we have to adhere to that rule as well. So this radical has to be greater than 0. So for the domain, it cannot be equal to negative 2 or positive 2, or any numbers between those, since that would then make this radical negative, and we cannot have that either. So since the numerator has no restrictions in the domain, and the denominator has restrictions, then that means the overall domain for the fraction is the part with the restrictions. Since this domain is included in the domain of the numerator and the domain of the denominator, then this is our answer. Okay, so keep this in mind when you're dealing with fractions. The domain will be the x values that overlap both. So let's walk through an example together. Let's say you're asked to find the domain of f of x, which is equal to the square root of x minus 7. Step 1, set the radicand or the expression underneath the radical sign, to greater than or equal to 0. So we have x minus 7 is greater than or equal to 0. And then we will solve for x. So we do so by adding 7 to both sides, showing us that x is greater than or equal to 0 plus 7, which is 7. So this would be our domain. It can equal 7, so we have the bracket, and that's the smaller value since it is greater than or equal to 7. 7 is the smallest number. And it continues indefinitely, so we have infinity as the second entry here. So that is how we go about finding the domain when we have a variable in the Radicand. Let's now have you complete a few practice questions. Question number 1, find the domain of f of x, which is equal to the square root of 2x plus 4. Question number 2, find the domain of g of x, which is equal to the square root of x squared minus 9. And question number 3, find the domain of h of x, which is equal to the square root of x plus 3 divided by the square root of 4x squared minus 36. Pause the video, answer these questions, and then press play when you are ready to begin. Question number 1, f of x is equal to the square root of 2x plus 4. So step 1, set the Radicand to greater than or equal to 0. And then solve for x. So we'll start by subtracting 4 from both sides, showing us that 2x is greater than or equal to 0 minus 4, which is negative 4. And now we want to divide both sides by 2, showing us that x is greater than or equal to negative 4 divided by 2, which is negative 2. So the answer to question number 1, in our domain, the smaller entry is negative 2, with a bracket to the left of it since negative 2 is included. And the larger entry is infinity, with parenthesis to the right. So this would be the answer to question number 1. Let's now have a look at question number 2. We were given g of x is equal to the square root of x squared minus 9. So step 1, set the Radicand to greater than or equal to 0. So we have x squared minus 9 is greater than or equal to 0. And now step 2, solve for x. So we'll begin by adding 9 to both sides, showing us that x squared is greater than or equal to 0 plus 9, which is 9. And to get rid of this exponent 2, we want to take the square root of both sides. So this creates a unique case where now we have x is less than or equal to negative 3 and x is greater than or equal to 3. Why is that? If x is negative 3, we'll have negative 3 squared, which is 9, minus 9, which is 0. So that's allowed. The Radicand can be 0 or greater. It just cannot be negative. So let's say this were greater than negative 3, but less than 3. So essentially negative 2, negative 1, 0, 1, or 2. 0 squared would leave us with negative 9. So that's not allowed. That would give us an imaginary number. 1 squared would be 1 minus 9, which gives us negative 8. So that's not allowed. And 2 squared would be 4 minus 9, which is negative 5, and that's not allowed. Negative 4, which would be negative 4 squared, which is 16. That would create a positive result and a real number. So our domain is x's that are less than or equal to negative 3, and x is greater than or equal to 3. So our domain, our first interval, is from negative infinity to negative 3, including negative 3, and positive 3 to positive infinity, including positive 3. So that is the answer to question number 2. Let's now have a look at question number 3. h of x is equal to the square root of x plus 3 divided by the square root of 4x squared minus 36. So in the numerator, we have a radical. So we will have a restriction with this expression since we cannot have a negative radicand. So we want to set the radicand in the numerator to greater than or equal to 0. This radical can be equal to 0 in the numerator since you can divide 0 by a number. We just cannot get 0 in the denominator since that would be undefined. So x plus 3 is greater than or equal to 0, and then we solve for x by subtracting 3 from both sides. So x is greater than or equal to 0 minus 3, which is negative 3. So this is the first restriction we're working with. X is greater than or equal to negative 3, so we'll put that to the side. And now we want to focus on the denominator. So we want to set the radicand in the denominator to greater than 0. And then solve for x. So we will add 36 to both sides, showing us 4x squared is greater than 0 plus 36, which is 36. And now we get rid of the coefficient 4 by dividing both sides by 4, showing us that x squared is greater than 36 divided by 4, which is 9. And now we take the square root of both sides to get rid of this exponent 2, giving us the square root of 9, which is positive 3 and negative 3. So we will get x is less than negative 3. Since we're squaring it, negative 3 squared would give us 9. Positive 3 squared would give us 9. Negative 4 squared would give us 16. Positive 4 squared would give us 16. But we cannot use numbers that are greater than negative 3 or smaller than positive 3. So the numbers between. So for example, 2 squared would be 4. 4 times 4 would be 16. 16 minus 36 would give us negative 20. And we cannot get a negative radicand. So now we have 3 different restrictions that we are working with from the numerator to our denominator. So what we want to do to figure out what our domain is for this one, we want to use a number line to see where these overlap. So our first domain, negative 3 to positive infinity, we plot that on a number line. Then our second portion of a domain is from negative infinity to negative 3, but not including negative 3. So that's here. Got the blue here, have the gray here for the first domain. And now the third portion we have from 3 to positive infinity, but not including 3. So that's here. So this domain is for the numerator, negative 3 to positive infinity. And then in the denominator, the domain is broken up into 2 parts. This first part from negative infinity to negative 3, but not including negative 3, does not overlap at all with the domain from the numerator. But this portion of the domain from the denominator, because these both came from the denominator, this portion of the domain in the denominator here does overlap this portion of the domain in the numerator. So from 3, but not including 3, to positive infinity, that is where our overlap exists. So that is the domain to h of x.